All right, so we're going to take a look at implicit differentiation in Notes Video D, Section 2.5. So just know I'm working out of Section 5 in Chapter 2. I'm looking at the topic of implicit differentiation. So if you need some extra background, you can certainly look in that section and read through some examples. All right, up until this point, we've been dealing with explicitly defined equations. Explicit. That means your equations are solved for y. We're working with functions. So some examples would be y equals 3x squared minus 5. And we can visualize that. It's a parabola, opens up, certainly passes the vertical line test. We've been working with explicitly defined equations. Another example.
Priscilla Lopez.
Okay, another function that's explicitly defined is y equals 1 over x. You can think of that reciprocal function. Perhaps you can even visualize it and know that it is a function that passes the vertical line test. Well, not all of the functions that we work with in this year are going to be explicitly defined. And I really shouldn't say functions, but some will be. Some of the equations that we're going to be working with are implicit equations, meaning they're not solved for y. Here's an example of an equation that's implicitly written. Now, this problem would be easy to solve for y. I could define it explicitly if I solved it for y by dividing both sides by x, and then the normal differentiation rules apply. Because the objective in this lesson is to take an equation that's implicitly written and find its derivative. And so what happens if we have another example that looks something like this, that's written implicitly, and we're unable to solve it for y. So just kind of think about this equation right here. You have y to the first and y cubed. Well, it's going to be difficult, impossible to solve this equation for y and find the derivative as we've been doing, because that's our objective. So we need another method, hence what we call implicit differentiation, to find the derivative of these implicit equations. So first I wanted you guys to look at the difference between explicitly defined functions and then implicitly written equations. All right, let's do some other review as well. All right, so far what we've done this year is we found derivatives of explicitly defined equations, and perhaps we're working with x squared. So consider y equals x squared, and consider finding the derivative. That's what this operator means, the derivative of x squared. Easy enough. We're going to get 2x. Okay, so what we have here, take a look at this, is we have a matchup. We have a rate of change with respect to x of x squared. So we just applied the normal power rule and we're good to go. Okay, well, let's look at another example. Maybe our letter of choice isn't x, maybe our letter of choice is y. So we want to find the rate of change of y. Oh, sorry, excuse me. We want to find the rate of change of y cubed with respect to y. So again, notice that these variables match up. Okay, so we're going to apply the power rule, 3y squared. Okay, something else that we've been doing this year too is, okay, we've been finding the derivative with respect to y, of an equation. So just imagine, if you will, if y was equal to something and we brought in the derivative operator. Okay, what does that look like in the line down? Well, it's just simply dy dx. Notice these variables don't match up here. X and y don't match up. We're finding a rate of change of y, some equation with respect to x. So that turns our notation into a y prime, if you will. So remember, we can also call this y prime. So these variables agree, these variables agree, these variables disagree here. So we didn't have a derivative here because the variables agreed. We didn't have a derivative in our answer because these variables agreed. But our answer is a derivative here because these variables did not agree. All right, let's look at another example. Okay, what happens if we were going to find a rate of change with respect to x of y cubed? X and Y don't agree. This is where the chain rule comes in. We don't have to do the simple power rule on these two, but we actually, in fact, did use the chain rule here, but we didn't say it exactly. Okay, right here, variables don't match up. All right, well, let's just go ahead and differentiate as if they did match up. So this derivative would look like 3y squared. Okay, but since they don't match up here, we say, okay, well, the derivative is 3y squared times the rate of change of y, the inside function. So think of now x cubed being the outside function. The inside function is y. So it's the derivative of the outside, power rule, 3y squared. Leave the inside alone, leave the variable y alone, times the derivative of the y with respect to x, times the derivative of y with respect to x. Well, again, we know this is just y prime. So actually, working across as opposed to down, I'm going to have 3y squared times dy dx. Okay, I just bring this up here, and I have dy dx. I think the author might have used y prime instead as the notation, and that's perfectly fine. But the problem that I have with that is I'm going to prefer to use dy over dx just because over here, if it almost looks like it's 3y squared times y to the first. And in that case, I would be tempted just personally to write it as 3y cubed. Okay, so I'm going to kind of distinguish the derivative by using the notation dy dx. All right, before we jump into some problems, let's continue practicing this kind of notation. Okay, so I have some examples here. Actually, I'm going to go ahead and pause, write them all out. Once you see them here, you might want to pause the video and write them all out too, and then we can solve them together. All right, continuing to look at some different problems that we might encounter. I have here for you 5 examples. 5 examples, and what we want to pay attention to is the matchup of the variables, and if we have to use the chain rule or not. Okay, so let's go ahead and start with example A. Rate of change of x cubed with respect to x. Variables agree. Simple power rule, 3x squared. I could, if I wanted to, I could multiply by the derivative with respect to x of the inside function, which happens to be the letter x. Well, if you think about this right here, it's a rate of change of x with respect to x. This would look like dx over dx. That would simplify to 1. 1 times 3x squared is just 3x squared. So when the variables agree, we're technically applying the chain rule. It's just that we're multiplying by that clever form of 1 here. All right, example B. What do we have here? We have disagreement. So chain rule, derivative of the outside function, 21y squared times the derivative with respect to, take a look back, x, of the inside function. So the outside function was 7y cubed, the inside is y, times the derivative of y with respect to x. This doesn't make a 1, this makes a y prime. I'm not going to use y prime. Again, like I said, that looks too much like y to the first, so I'm just going to write down times dy over dx. So we need this notation to help us when we go to solve problems in the next video. All right? All right, so studying this example right here, I see that I have a derivative operator on 2 terms. That requires the sum and difference rule that we've been working with. So when you apply the derivative operator here to x, we know that derivative is just 1. Variables agree, we're done. Minus, look at the derivative of 5y. Well, you can think of it as a constant multiplier rule, or you can think of it as the power function, 5y to the first. So the derivative of this term, okay, if you're applying the power rule, would be 5y to the 1 minus 1, 0, which is just going to be 1, times, because these variables don't agree here, times the derivative with respect to x of the inside function, which happens to be y. A little cleanup would move us over here. 1 minus, that goes to 1, 5 times dy dx. All right, continuing here. All right, when I studied this implicit term, I'm noticing there's a product. So I'm thinking, because I need to find the derivative of a product, to me, I'm thinking product rule. So let's kind of identify my factors. So I have f, and then I have g. So first, times the derivative of the second, derivative with respect to x of the second factor. Let's worry about performing the calculations in my next step. Plus the second factor, y to the fifth, times the derivative of the first factor, 3x squared. All right, to save space, I'm just going to work across here. Okay, we're going to take care of this derivative here. So studying this, variables disagree, chain rule. So we'll apply the simple power rule first, and then multiply by the derivative of y with respect to x. So coming over here, keep 3x squared, this derivative, times 5y to the fourth, times the derivative with respect to x of the inside function, which is y. Okay, I'm right here at the plus sign, with the addition sign, plus. Okay, y to the fifth. And the variables agree here, simple derivative, simple power rule, it's times 6x. And here, I'm going to clean it up a little bit. So I'm looking at this whole group here. That's one term. That's one term. So let me see how I can clean that up. That's going to be 3 times 5 or 15 x squared, y to the fourth, and then here, times dy dx. And then plus, I'll do a little rearranging on this term. I'll put the 6 in front with the x with the y to the fifth. So that's my answer here. That's common practice to kind of put it in that order. Okay. So if you're taking a peek in at that last example, example E, okay, the necessary differentiation rules is going to require us to use the chain rule. So it's a composite function. So the derivative of the outside, leave the inside alone. So bring the 3 in front, drop that to 2. I'm not done until I say I'm going to multiply by the derivative of what I left alone, the inside function. Bringing this part of the problem down, I'm done with it. It just kind of drags down. Okay, focus our attention here. Well, that's another sum and difference rule, kind of like an example C up here. So we're just going to apply the derivative operator to the two different terms. So variables agree. So the derivative is 6x. So remember, this is all multiplication. This is a chain of factors because we're involved in the chain rule. So this derivative is 6x plus, if you apply the derivative operator here, you see the variables disagree. So it's going to be 4 times the derivative of y with respect to x. Okay, you can do it that way. We can think about the power rule and the chain rule, but this derivative would be 4 times dy dx. Okay, can you clean that up from here? Probably, but we're going to worry about that in the next video when we actually get to some examples and get to the calculus piece of trying to write equations of tangent lines, trying to find vertical tangents, trying to find horizontal tangents, things of that nature. Okay, so this was just more of an exercise in looking at the notation and making sure that we know how to handle it. Okay, so we're going to stop here, and in the next video, we'll look at some specific examples that apply to what we need to do.